Welcome back everyone to this lecture on backpropagation. The last theory topic we're going to cover is backpropagation, and we're going to start by trying to build an intuition behind backpropagation, and then we'll dive into the calculus and notation of backpropagation. I want to point out that backpropagation is probably the hardest part of the entire theoretical deep learning process because of the calculus and the notation involved with that calculus, especially when we start talking about backpropagation in dealing with a matrix of weights and another matrix of biases. So keep that in mind. This is going to be pretty difficult, especially if you're rusty on your calculus notation. With that in mind though, if you understand the basic intuition that you basically just move backwards through a network to update the weights and biases, then that's actually enough to continue on with the rest of the course. So if you're fuzzy on the calculus portion of this lecture, don't worry too much about that because it's not like you're going to be needing to compute the gradients yourself. The actual code is going to do that for us. So fundamentally, we want to know how the cost function results change with respect to the weights in the network. That way we can update the weights to minimize the cost function. And we already talked a little bit about that when talking about things like gradient descent and how it approaches the cost function. So let's go ahead and begin with a very simple network in order to understand backpropagation. So this is a super simple network. Essentially, each layer only has one neuron. So we'll see how backpropagation works with just a network of a couple of neurons, and then we can easily expand this to networks with multiple neurons per layer. So, as we already know, each input basically receives a weight and a bias. So there's an incoming weight attached to that edge, and then each node, or that is to say each neuron, has its own bias. So we get the sort of formula weight 1 plus bias 1, weight 2 plus bias 2, weight 3 plus bias 3, and so on. So this means that we have some sort of cost function that's dependent on those weights and biases. And we've already seen how this process propagates forward. So let's go ahead and start at the end to learn about backpropagation. So we already noted that the way we notate layers is by having the very last layer be called L. So then our notation becomes that the neuron all the way on the right is in layer L, the neuron to the left of it is L minus 1, L minus 2, and so on for L minus n layers. Now let's go ahead and just focus on the very last two layers of our network because backpropagation starts all the way at the end of the network at layer L once we've gone through our feed forward process. And when focusing on these two layers, I want to remind ourselves of the notation we've been using. So far we've been defining z as w times x plus b. And x, recall x, that notation of x, that's really only valid at the very first layer because x stands for the actual raw feature inputs. As you keep going from neuron to neuron further into the layer, x technically becomes the output of the previous neuron, which is defined as a. Because remember, after we apply an activation function to z, such as sigmoid of z, we label that as a. So as you go further and further along into these layers, z would actually be z equal to w times a plus b, because x is technically only valid at that very first layer as the raw feature input. Once you actually pass that into a neuron, you're technically not dealing with the raw features anymore. Instead, you're dealing with the output of the previous neuron's layer, which is better stated as a, the sigmoid of z, or whatever activation function you choose. Okay, so what does that actually mean when we take it into account for that very last layer? Well, that means that z at the last layer is going to be equal to those weights at the last layer times a of L minus 1. So what is a of L minus 1? Well, a of L minus 1 is simply the output of that previous layer's neuron. So a L minus 1 plus b of L, the biases at that very last layer. So again, a of L, so the activation function output at that very last layer, is equal to sigmoid, or the activation function, of z of L. So notice how z of L is defined by the weights and biases at that layer L, and then it's defined by the output of the previous neuron. So hopefully you can kind of make these connections. And that means that then the cost function is going to be equal to a of L minus y, where y is the actual true output, squared. So what we actually want to understand is how sensitive is the cost function to changes in w. And this is where partial derivatives come into play, because we want to figure out the relationship between that final cost function and the weights, in this case, at the layer L. So we're going to say take the partial derivative of that cost function with respect to weights and layer L. And if you know some calculus, then you know that there's a chain rule. And so if you were to take the formulas we just saw here and apply the chain rule for them in order to solve for this partial derivative we mentioned here, because we want to understand the relationship between that cost function and the weights in the network, then you end up calculating this formula. So this is just the chain rule. It basically allows you to take the derivative of a function within a function. So here, using some calculus for the chain rule, we can determine that the partial derivative of that cost function with respect to that weights is equal to the partial derivative of the z with respect to the weights times the partial derivative of the a with respect to z times the partial derivative of the cost function with respect to a. Essentially, the chain rule allows us to pull apart these functions within functions, because we saw from these previous three formulas that the cost function is defined by a of L is then defined by z of L, and then z of L is defined by w of L and b of L. Now recall that the cost function is not just a function of the weights, but it's also a function of the biases. So we want to be able to understand the relationship of the cost function changing not only with the weights, but with the bias along the network as well. So we can then calculate the same partial derivative, so the partial derivative of the cost function with respect to those bias terms, in the same way, essentially just kind of swapping out that weight for the bias. Now the main idea here is that we can use the gradient to go back through the network and adjust our weights and biases to minimize the output of the error vector on that last output layer. And recall that the gradient is essentially that derivative when you're dealing with n dimensions. So using some calculus notation, we can expand this idea to networks with multiple neurons per layer. And there's going to be some notation you'll see in just a little bit, which again, if you're a little rusty on linear algebra or calculus, it's called the Hadamard product. And it's actually a product that you're already familiar with because it's kind of the default with NumPy and these different deep learning libraries where you're actually performing an element by element multiplication. So again, the Hadamard product, that little dot notation that kind of looks a little bit like a hydrogen symbol, basically what it means is just do an element by element multiplication. And that means that the two matrices should be the exact same size, which makes sense because that's going to match up for things like weights and biases. So given this notation and backpropagation, we just have a few main steps to train neural networks. Now note again, you don't need to fully understand these intricate details on calculus or the notation to continue on with the coding portions of this course. Let's review now the actual learning process for a network. We start off with just a very basic feed-forward process that we're already familiar with. In step 1, using that input x, that is the original features, we set the activation function a for the input layer. So that very first input layer then means that we have z is equal to wx plus b, and then a, that output essentially coming out of that input layer, is going to be equal to your activation function of z, in this case represented as sigmoid of z. So this resulting a then feeds into the next layer. So then you have the next layer taking in a, which means its z is going to be w times a plus b of the previous layer. So then you go into the next layer, and then you take the output of that a, stick it into z, then so on and so on. So if we think about this, for each layer, all we're doing is we're computing those z's and those a's, since a is based off z. So if I'm at some layer L, then what I'm going to be doing is setting z of my current layer L equal to the weights at L times the output from the previous layer, that is a of L minus 1, plus the biases of my current layer, b of L. Once I have my z of L, I'm going to pass that through my activation function, in this case sigmoid, and then I get the a of my current layer L. And then I can pass that to the next layer of L plus 1, and so on and so on. And then we come to step 3. And here we've written it out in the full calculus notation of computing our error vector. But essentially what we want to do is, if you take a look and focus on just that very first term, all this is doing is essentially expressing the rate of change of that cost function with respect to the output activations. And in the case of the quadratic cost function, then that's essentially the same thing as saying the activation of the last output layer minus y, which was the true value. And essentially what we want to do is be able to calculate this error vector and back propagate it, essentially calculating the error back through every other single layer. That way we can adjust the weights and biases for that error. So replacing that first term with a of capital L minus y, we get the following formula. And again, we're using that Hadamard product here. So what I want to do is I want to write a generalized error vector formula. And I'm going to write it out in terms of the error in the next layer, which makes a lot of sense because all we're doing is we're moving backwards. And a real quick note here is it's a little tricky to find a font where a lowercase l looks different than the number 1. So I have 2 little bullet points there to show you what I'm talking about. So a lowercase l essentially looks like a straight line. The number 1, it has a little dash on top. So keep that in mind as you see what's happening next. The reason I'm not going to be using a capital L is because in general we should be using capital L to denote the very last output layer. And what I want to do is show you the formula for the error vector and those calculations for any layer L, lowercase l that is, inside of the network. So what I'm going to do is for this back propagation step, for every single layer, starting at the very last layer, capital L, then moving to capital L minus 1, capital L minus 2, etc., all the way for all these layers, the generalized then error term, so that error term, that delta to the little l, or lowercase l, is going to be equal to the weight matrix, L plus 1, that's the lowercase l, then transpose that, so that t, that term right there, that's the transpose of the weight matrix in the next layer on the right-hand side of the L plus 1. That's the lowercase l. And then we have there multiplied by the error term at that also next layer. And then we take the Hadamard product again with the z of l passed into the activation function. So again, all we're doing there is back propagating the error, and here we have the generalized error for any layer lowercase l. So when we apply that actual transpose weight matrix, that weight matrix of L plus 1 transposed, we can think intuitively of this as moving the error backward through the network, giving us some sort of measure of the error at the output of that Lth layer. We then take the Hadamard product of that times the Hadamard product there of the z at that layer passed into the activation function. And what this does is then this moves the error backward through the activation function in layer L, giving us the error in L in the weighted input to layer L. So again, that's a generalized term, which is why you see me using that lowercase l. And then we can understand that the gradient of the cost function is given by these 2 formulas. So then for each layer, L minus 1, L minus 2, and so on, all we're really doing is computing that partial derivative of the cost function with respect to the weights and the biases there. And J and K, that's just notation for the actual neurons themselves. This then allows us to adjust the weights and biases to help minimize that cost function. So I know this was quite difficult to understand in terms of the notation of the calculus, and don't worry if you didn't get it right away. This usually takes, at least for me, it took definitely a couple of hours to understand, just trying to write it out with paper and pencil. So what I've done is I've linked to you in this lecture some external links. You should see it as a little folder pop up as you're kind of watching this lecture, or right next to the lecture title, you should see a little drop-down folder you can click. There's some external links there that actually go and essentially derive step by step all these equations. So if this overview wasn't enough for you and you want to see every step and the whole derivation of this process, plus the proof of those kind of 4-step fundamental backpropagation equations, check out the external links for lots of details on that. But if you have the general understanding that you're basically calculating the error term at the very last layer and then going backwards through the network to calculate all those errors and then adjusting the weights and biases accordingly to minimize that cost function, if you understand that general intuition, you know enough to go ahead and continue with the course. All right, thanks, and I'll see you at the next lecture.